The performance of centrifugal pump is very important for understanding of the behavior of pump for particular operating condition. The performance is affected due to various factors. These factors are speed, diameter, outlet blade angle, and density of the fluids. So today's discussion includes, in addition to these above factors, I will also discuss some basic theories which are linked with the performance of centrifugal pump. So let's begin the discussion. These are the topics: Euler head and energy transfer relationship, flow and head rise due to speed and diameter change, Euler head in blade angle form, flow versus head curve for different types of impeller, flow versus head and flow versus pressure curve for backward impeller, and finally the performance of centrifugal pump. Euler head and energy transfer relationship. In the previous discussion, we have now understood that energy head given to the fluid is expressed as energy head is half into C2 square minus U1 square plus U2 square minus U1 square plus V1 square minus V2 square, and Euler head is U2 into CW2 minus U1 into CW1. For the centrifugal pump, as flow is in the axial direction, and so CW1 is 0. So this term will be 0. So we can write Euler head is equal to U2 into CW2. So we need to prove that energy head, which is equal to half into bracket start C2 square minus C1 square plus U2 square minus U1 square plus V1 square minus V2 square bracket close is equal to Euler head, which is equal to U2 into CW2, where C1 C2 inlet mean outlet absolute velocity meter per second, V1 V2 inlet mean outlet relative velocity meter per second, U1 and E2 inlet mean and outlet tip velocity in meter per second, CW1 CW2 inlet mean and outlet whirl velocity or tangential velocity in meter per second. Now relationship. This is inlet velocity triangle drawn on in impeller. So same thing is written here. So using this triangle, we can write C1 square is equal to V1 square minus E1 square. So we can write C1 square plus U1 square minus V1 square is 0, dividing half on both sides. We can write half into C1 square plus U1 square minus V1 square is equal to 0. This is equation number 1. Now for the Euler head for outlet velocity triangle, this is outlet impeller outlet velocity triangle, and this is same thing written here. If you look at on the right hand side of triangle, CA2, this is CA2 square is equal to C2 square, this is C2 square minus CW2 square, and also on the left hand side, if you see, CA2 square is equal to V2 square minus this square, which is U2 minus CW2, so U2 minus CW2 square. So further you can replace CA2 by this. We can write C2 square minus CW2 square is equal to V2 square minus bracket start U2 minus CW2 square. So on simplification, we can write half into C2 square plus U2 square minus V2 square bracket close is equal to U2 into CW2, equation number 2. Subtracting equation number 1 from the 2, we can write half into C2 square minus U1 square plus U2 square minus U1 square plus V1 square minus V2 square is equal to U2 into CW2. So this is the expression for Euler head in terms of energy transfer to the fluid. Now flow and head change due to speed and diameter. This is a standard flow equation coefficient. So inlet flow coefficient is defined as the ratio of inlet actual flow and product of speed and circular area of outer diameter of impeller, which is written as inlet flow coefficient phi is equal to q upon pi by 4 d square into u2, and u2 is consisting pi d into n. So in this, using this expression, it can be derived as inlet actual flow, that is q, is proportional to a speed for constant diameter, because u2 contains a speed. So q is proportional to a speed. So q2 by q1 is equal to n2 by n1. In inlet actual flow is proportional to cubic of diameter of impeller for constant speed. Here, if speed is constant, so d square and u also contains d, so dq. That is why it is written as q is proportional to cubic of d. So q2 by q1 is equal to d2 by d1 to the power 3. So in actual flow is proportional to the speed and cubic of diameter of impeller, for both are variable. So we can write q2 by q1 is equal to n2 by n1 into d2 by d1 to the power 3, where q is inlet flow, volumetric flow, meter cube per second, n is the speed of impeller, rpm, d is the outer diameter of impeller in meter, phi is inlet flow coefficient constant, u2 is impeller outer outlet tip velocity in meter per second. Now hydraulic head coefficient is defined as the ratio of hydraulic head and product of half and square of tip velocity. So head coefficient psi is equal to h upon half into u2 square. Since u2 contain speed and diameter both, so it square of diameter and speed. So from this expression, hydraulic head is proportional to the square of speed of impeller for constant diameter. So h is proportional to square of the speed. So we can write h2 by h1 is equal to n2 by n1 to the power 2, and hydraulic head proportional to square of diameter, not the speed, by mistake it is written for constant speed. So h is proportional to d square. So h2 by h1 is equal to d2 by d1 to the power 2. So hydraulic head is proportional to square of the speed and square of diameter of the impeller, if both are variables. So h2 by h1 is equal to n2 by n1 to the power 2 into d2 by d1 to the power 2, where h is hydraulic head in joule per kg, n is just speed of impeller, and rpm, d is outer diameter of impeller in meter, psi is head coefficient constant, u2 is impeller outlet tip velocity in meter per second. So these are the expression for head rise or hydraulic head rise for variable of speed and diameter both. Now Euler head in blade angle form. Using the outlet blade angle, outlet velocity triangle, the dotted line is for ideal case where slip factor is not considered, and solid line is the actual case where slip factor is considered. Euler head we know U2 into CW2, but slip factor sigma is equal to CW2 upon CW2 dash. This is as per definition. Slip factor sigma is CW2 upon CW2 dash. So CW2 can be written sigma into CW2 dash, but CW2 is equal to U2 minus this. So you can write U2 minus C. What is this value? This value is V2 dash into sine beta 2. So you can write CW2 is equal to U2 minus V2 dash sine beta 2. But what is V2 dash? V2 dash is a Q upon A2. Q is a actual flow, outlet actual flow. Since flow is same inlet and outlet, so we can write Q upon A2. A2 is the cross-sectional area, outlet cross-sectional area perpendicular to ideal outlet relative velocity. So CW2 can be written as U2 minus Q by N. We can replace V2 dash is Q by A2 into sine beta 2. Now CW2 is equal to sigma into CW2 dash. So sigma into this, we can write sigma into bracket start U2 minus Q by A2 into sine beta 2 bracket close. Euler head can be written as U2 into CW2. So U2 into CW2, this is written here. So finally, we can write Euler head H is equal to sigma into U2 square minus sigma into U2 upon A2 into sine beta 2 into Q. This is the most important equation for understanding of flow versus head change for different blade angle. Further, we can write Euler head H is equal to sigma into U2 square minus sigma into U2 upon A2 into sine beta 2 into Q. So now let us understand express in another form of A2. So gap between two blades at impeller outlet and perpendicular to ideal relative velocity is expressed as B2 is equal to pi d cos beta 2 upon n minus T2 in millimeter mm. Cross sectional area perpendicular to ideal relative velocity at impeller outlet A2 is equal to n into B2 into WD2 upon 10 to the power 6 in meter square. So further we can write A2 is equal to, by replacing B2 with this, we can write pi d cos beta 2 minus NT2 bracket close into WD2 upon 10 to the power 6 meter square. Slip factor sigma is equal to 1 minus square root of cos beta 2 upon n to the power 0.7. So A2 depends on diameter, blade angle, number of blades and outlet blade thickness and WD2, and sigma depend on blade angle and number of blades. So if you see this equation for particular geometry, particular blade angle, H depends on only the flow and which is starts decreasing. So from the above expression, it is evident that head rise, that is Euler head rise, depends on flow for particular impeller geometry and speed, because U2 contains a speed and diameter both. It can also be said that for the change of outlet blade angle, head rise, that is Euler head, also changes for particular flow. When outlet blade angle is smaller, head rise will be more, and when angle is larger, head rise will be less for particular flow. Where H is Euler head in joule per kg, Q is inlet actual volumetric flow meter cube per second, U2 is impeller outlet tip velocity meter per second, N is number of blades, WD2 is impeller outlet blade width in mm, D is impeller outlet diameter and in millimeter, and T2 is impeller outlet thickness and in millimeter. Beta 2 is outlet blade angle, in degree sigma is slip factor. Now flow versus head curve for impeller types. Three types of impeller are possible, that is backward blade impeller, radial blade impeller and forward impeller. This is a backward impeller blade angle measured from the radial direction beta 2. So direction rotation in opposite direction. This is blade angle on this side, direction rotation is this side. So this is called the backward impeller. This is radial direction, beta 2 is 0 and rotation has no much impact on this. This direction is radial. Forward impeller, the direction is the same direction of the blade, outer blade, you can see here. So, but beta 2 is measured from the radial, however, it can be measured from tangents also. But in this video, it is shown only measurement from the beta 2, which is from the radial direction. Backward impeller is blade angle is measured from 0 to 90 degree. So in between 0 to 90 degree is backward. A beta 2, so we can see sine value lies between 0 to 90 is always positive. So this term becomes negative. So with the change increase of the q, h starts decreasing as per this equation, because this term starts increasing, so this whole term will be decreasing. When beta 2 is 0, that is radial, in case q is not there in the equation, so it does not depend on the q, so it remains constant for variation of the flow. So when flow is increasing, there is no change of Euler head rise. In case of forward, the blade angle is lies between 0 to minus 90 degree. That means on 0 to 90 degree, minus 90 degree. But minus beta 2 is negative, so negative to negative is positive. So the whole term becomes positive. So with increase of the flow, head rise starts increasing as per this equation. So same thing, it is shown on the graph. This is x-axis flow, y-axis is Euler head rise, and if you see on the backward side, backward impeller head rise expression is this. You can see here, this is backward, it starts decreasing as per this equation when this whole term is constant but q is increasing, that is why h is decreasing. In case of radial impeller, since q is not present in the equation, that is why it remains constant. You see here, this is radial impeller graph. In case of forward, it is increasing because when q is increasing, this term is also increasing. So h is increasing. You can see here, h is also increasing. So from this, Euler head is smallest in case of backward and highest in case of forward impeller, and radial lies in between them. But in case of efficiency, it is a maximum in case of backward impeller and minimum in case of forward impeller, and radial lies in between them. So based on the above characteristic of impeller, since for the best efficiency point of view, backward curve blade impeller is always used for operation and control purpose, and beta 2 angle is always lies between 0 to 90 degree for backward impeller case. Now the flow versus head and flow versus pressure curve for backward impeller. This is backward impeller. Euler head is expressed same way, and beta 2 lies between 0 to 90 degree, and as flow increases, impeller starts Euler head starts decreasing as per this equation. So same thing it is shown here. X-axis is volumetric flow in meter cube per hour, and y-axis is Euler head in joule per kg. If you see, as flow starts increasing, head rise starts decreasing. This is point for maximum efficiency point. So we can say this is particular flow where particular Euler head rise at design point. Now this is curve for efficiency for backward impeller. Efficiency correction factor is maximum at design point, and it starts decreasing on if flow is lower side, lower than design, or if flow is more than design. Now the hydraulic head is equal to Euler head into efficiency. So the pattern will be approximately similar like Euler head. So this is curve, x-axis is a volumetric flow, y-axis Euler head. This is y-axis is a hydraulic head. So this is Euler head, and this is hydraulic head. You will see the gap is, this is a maximum because the efficiency is a maximum. On this side, gap is wider because efficiency is lower, and that is why Euler head is lower. Then it starts increasing because efficiency is increasing, and then again Euler head starts decreasing because efficiency is decreasing. Now in terms of flow versus pressure curve, x-axis is a flow, y-axis is discharge pressure, and discharge pressure is equal to inlet pressure plus hydraulic head into density of the fluid. So discharge pressure depends on inlet pressure and density of the fluid for constant hydraulic head. And you have also observed that when pump handles oil, discharge pressure is lesser than when it handles water, because density of oil is lesser than density of the water. So you can see from this expression, discharge pressure also influences the density of the fluid. So you can see here, this is a curve for particular condition where design condition. This is discharge pressure and this is the flow. The flow versus discharge pressure curve. Now the performance of centrifugal pump. The performance of pump depends mainly on impeller types, whether it is forward, radial and backward impeller. In addition to impeller types, outlet blade angle plays vital role, and which are responsible for pressure rise, because and then speed and diameter of impeller also plays a major role for performance of the pump. Last but not the least, the flow is key factor which decides the discharge pressure for fixed speed, diameter and blade angle. So let's discuss in detail for above each point. The performance following factors are responsible for performance of pump, that is variation in outlet blade angle, that is beta 2, variation of speed is n, and variation of outlet diameter, that is t. Euler head for backward impeller, for outlet blade angle, that is beta 2, lies between 0 to 90 degree and which is measured from radial. So Euler head sigma u2 square minus sigma u2 by a2 into sine beta 2 into q. So when outlet blade angle beta 2 is a lesser value, so sine beta 2 will be lesser. So whole term h will be larger. So head rise is more, that is Euler head is more for fixed flow. Similarly, when outlet blade angle beta 2 is more, then sine beta 2 will be more, so whole term will be more. So this will be less. And so head rise, that is Euler head, will be lesser for fixed flow. Lesser outlet blade angle means impeller is in towards the radial direction. Angle is towards radial direction, and which can cause more hydraulic head rise. For fixed outlet blade angle, when flow increases, Euler heads starts decreasing. This is as per this equation. When Q is increasing, other terms are remain constant, then head starts decreasing. Variation in outlet blade angle beta 2. So x-axis is flow in meter cube per hour, y-axis is Euler head, and for different blade angle. They all are backward blade angle but of different angle. That means one is design blade angle, one is lesser than design blade angle, and one is larger than design blade angle. If you see this, for the fixed or for the same design, or for the design condition we can say, or for the fixed flow, the angle which is smaller than design angle will produce more Euler head. We can see, you can see here red line. This one, this is blade angle which is larger than, sorry, outlet blade angle beta 2 is yes, this is larger than design point angle, will produce lesser Euler head, which is shown here. So even though all are backward blade angle, backward impeller, but even the beta 2 is changing, it will impact the Euler head for the particular flow, which can be seen from this graph. Now, Euler head, as I say in same equation. Now, if you want to calculate the hydraulic head, we need to multiply with hydraulic efficiency. It is changing with every flow as per the hydraulic head efficiency correction factor. So hydraulic head is equal to ES into bracket start sigma U2 square minus sigma U2 upon A2 into sine beta 2 into Q. So for the fixed outlet blade angle, hydraulic efficiency is a maximum design flow condition and it starts decreasing either less or more than design flow. So with increase of the flow, hydraulic head initially starts increasing, reaches maximum and then starts decreasing. For lesser outlet blade angle, hydraulic head will be more and vice versa. See, this is again hydraulic head. The y-axis, x-axis is the flow in meter cube per hour. Hydraulic head in y-axis joule per kg. So again, if you look at for particular flow, red line, that is angle beta 2, which has a lesser blade angle from the design, will produce larger hydraulic head, and blue line you can see which has blade beta 1, which has more blade angle, larger blade angle than design blade angle, will produce lesser hydraulic head for the particular flow. You can see here. So hydraulic head of blade angle 2 will generate or greater than hydraulic head of design blade angle, and which is more than hydraulic head of blade angle 1, which for particular flow you can see as per this graph. Same way, hydraulic head, now we can discuss in terms of pressure. So Euler head as can be expressed for this, and hydraulic head can be written as sigma, sorry, hydraulic head can be ES, that is efficiency, into sigma U2 square minus sigma U2 upon A2 into sine beta 2 into Q, and it has a relationship with the hydraulic density and inlet pressure, which can be written as hydraulic head is equal to discharge pressure minus inlet pressure divided by density of the fluid. And so from this we can write discharge pressure is equal to hydraulic head into density of fluid plus inlet pressure. For the fixed outlet blade angle, with increase of the flow, discharge pressure initially starts increasing, reaches maximum and then starts decreasing. This follows the similar pattern of hydraulic head. For lesser outlet blade angle, discharge pressure will be more and vice versa. Now let us see the graph. X-axis on the volumetric head, y-axis discharge pressure. You can see the blade angle beta 2. Blade angle 2 is less than blade angle 1, which is less than design blade angle, which is less than blade angle 1. All are measured from the radial. You can see the red line, which has blade angle lesser than design, will produce more discharge pressure, and blue line, which has blade angle greater than design, will produce less discharge pressure. For particular flow, you can see here. Now the variation for the flow versus coupling power, we can hydraulic head can be written like this, again ES into bracket start sigma U2 square minus sigma U2 upon A2 into sine beta 2 into Q, and pump power is equal to mass flow rate into hydraulic head upon hydraulic efficiency. So pump power further can be written is equal to inlet volumetric flow into density of fluid into hydraulic head upon hydraulic efficiency. So coupling power is equal to pump power plus mechanical loss power. For lesser outlet blade angle, coupling power will be more and vice versa, and for inlet flow and hydraulic head will also be more for lesser outlet blade angle. Outlet blade angle, again you can see here, x-axis is the volumetric flow, y-axis coupling power. You can see for the fixed flow, red line which can consume more coupling power than blue line, or from design point. So blue line will consume less coupling power from the design, and red line will consume more coupling power from the design. This is because red line will have less blade angle, which can produce more head rise as compared to design, and blue line will produce have a large blade angle and produce less head rise, and that is why less coupling power. This is as per expression. Now variation in the speed. Inlet actual flow volumetric flow is proportional to speed. So of design volumetric flow is equal to design flow into n of design divided by n design. So Q of design is equal to Q design into n of design upon n design. When a speed is less than design speed, the inlet volumetric flow will be lower than design volumetric flow, and when a speed is more than the design speed, inlet volumetric flow will be more than design inlet volumetric flow. This is as per expression this. Hydraulic head is proportional to square of the speed. So of design hydraulic head is equal to design hydraulic head into n of design divided by n design to the power 2. So h of design is equal to h design into n of design upon n design to the power 2. Hydraulic head has a relationship with inlet and discharge pressure with density. That means hydraulic head is equal to discharge pressure minus inlet pressure into divided by density of the fluid. So discharge pressure is equal to hydraulic head into density plus inlet pressure. So when the speed is less than design, discharge pressure will be less than the design pressure, and if the speed is more than design, discharge pressure will be more than design discharge pressure. And it also depends on the density of the fluid. The higher the density, higher is the discharge pressure, and vice versa. This is as per the expression. This density is also multiplied here. Pump power is equal to mass flow rate into hydraulic head upon hydraulic efficiency. So pump power is equal to inlet volumetric flow rate into density of the fluid, which is equal to mass flow rate into hydraulic head divided by hydraulic efficiency. So coupling power is equal to pump power plus mechanical loss power. So now we can see here, this is graph for three different speed. Red line is a more speed than the design, blue line is a less speed than design, and you can see for particular flow discharge pressure is a more in case of red, where speed is more, and blue line, which has a less than design, will produce less discharge pressure as per the graph. Now coupling power for the particular flow, coupling power for the red line where speed is more will consume more coupling power than the design, and blue line will consume less coupling power than the design, because with the more speed it will produce more discharge pressure or hydraulic head. Variation in diameter. Inlet actual volumetric flow is a proportion to cubic of diameter. So of design volumetric flow is equal to design flow into d of design upon d design to the power 3. Q of design is equal to Q design into d of design upon d design to the power 3. So when outer diameter is less than design, actually not speed, design diameter, wrongly written speed, design diameter. Inlet volumetric flow will be lesser than design volumetric flow. If outer diameter is more than the design speed, again wrongly written, design diameter, then inlet volumetric flow will be more than design inlet volumetric flow. Hydraulic head is proportional to a square of outer diameter. So we can write of design hydraulic head is equal to design hydraulic head into d of design upon d design to the power 2. So h of design is equal to q design, sorry, h design into d of design upon d design to the power 2. So hydraulic head has a relationship with inlet and discharge pressure with density. So same way we can write discharge pressure is equal to hydraulic head into density of fluid plus inlet pressure. So when diameter is less than the design diameter, discharge pressure will be lower than design pressure and vice versa. It also depends on density of the fluid because density is multiply higher the density, higher the discharge pressure and vice versa. So pump power is equal to mass flow rate into hydraulic head divided by hydraulic efficiency. So pump power is equal to inlet volumetric flow rate into density of fluid into hydraulic head upon hydraulic efficiency. So coupling power is equal to mechanical pump power plus mechanical loss power. So x-axis a graph is drawn. X-axis is for volumetric flow, y-axis is discharge pressure. You can see in the graph, red line will have a larger diameter, will produce more discharge pressure. Blue line will have lesser diameter, then the design will produce less discharge pressure. And this is as per the expression seen just before. So larger diameter will produce larger discharge pressure. Now the x-axis is flow and y-axis is for the coupling power graph. Again, the larger diameter, that is red line, will consume more coupling power than diameter D1, which has lesser diameter. So because larger diameter will produce more hydraulic head as per expression just seen before. So hope you have understood the performance of centrifugal pump and how the head, Euler head, hydraulic head and pressure changes with the change of blade angle, with the change of speed, and with the change of diameter. But pressure is sometimes also affected due to density of the fluid. And so I hope you like this, and thank you for watching.